Hi everybody, it's Mrs. Cassill. I know that there were some questions about how to use Newton's laws to find the force of friction, and in particular your coefficient of friction in this example. So we're going to go ahead and work through that. I'm going to go over a few things first. The first one being, how do you find a net force? You may think that you're not solving for net force in here, but anytime that you want to be able to use Newton's second law, you are relying on the fact that Newton's second law says a net force is equal to a mass times an acceleration. So even in a problem like this, where force of friction isn't the net force, it's just one of the forces, you're going to need to find that net force in order to utilize this equation to yield its full power. So there's a couple steps to solving any free body diagram, any net force related problem. The first one is that you always want to draw a free body diagram, right? So the first thing you're always going to do is draw that free body diagram. Try to draw it as accurately as you can and include as many details and labels. Second thing that you're going to do is you're going to break your forces into components. So you're going to look at every single force that you have there in your coordinate system, and you're going to figure out what the x and y component of each of those forces is. After that, redraw your free body diagram, even though that might seem like a redundant step. But if you redraw your free body diagram, it's a nice reality check in the middle of your problem. It makes it easy to see if you've got forces in the right direction, and you can make some estimations about what will happen as a result. You can also then easily, graphically or mathematically, sum the forces in the y direction and the x direction. So you've got sort of this first step here where you're summing the forces, and then forces are vectors. So then you're going to need to actually find net force, which is summing the vectors again, summing force again, right? But so then you need to find your net force using those x and y components. Okay, so those are the 5 steps to solving any problem that includes net force. So let's go ahead and go through this process with your scenario that you have here. Okay, you've got a ramp like this. You've got an incline, whatever it is that you've used. It's at some angle theta. I measured this with my the level on my phone rather than a protractor. Much more accurate, honestly. And you've got your object that's sitting on top of your ramp here. Now, this isn't a free body diagram, right? This is a picture, but this helps me when I'm understanding a problem. There's a couple things about this lab that are important to realize. It is moving downhill, right, parallel to the surface with a velocity that's constant. So I've got a constant velocity going down the hill. That tells me a few things. That means the acceleration on the ramp is equal to 0 in the scenario that we're analyzing here. So we're going to come back and use that fact to help us. There's a couple other triangle things to remember, right? The sum total of the angle degrees in a triangle is 180. And we use that to figure out what some of our other angles are. For example, this angle here is 90 minus theta, right? Because we have 90 degrees here, which means these other two must add up to 180 minus 90, 90 degrees. This angle's theta, so I had a total of 90 minus theta. That's what's left over for this angle right here. So those are a few things that we know about this situation. I want to offer you one more hint in just a moment here, which an angle makes things confusing. I'm going to use this angle in a different way, which is going to help you understand the physics of what's happening here. Okay? So I'm going to draw my free body diagram now. Okay, so that was just my story problem of the scenario, right? Now I'm going to draw my free body diagram. I've got my box that's at some angle. I've got a couple of different forces that are acting on it. I always start by thinking, gosh, I'm on planet Earth. So I've got the force of gravity acting downward. That's a given. This object is not being pushed. doesn't have a jetpack in it. It is moving down the ramp because of the net force that's on it, but it is scraping along that surface, so it's resisting that motion with a force of friction that's directed uphill, right? This is parallel. If I kind of draw through here, I know that I've got this angle theta right here. Okay, so that's where this free body diagram, the shapes of this are coming from. It's resting on a surface, so that tells me that perpendicular to that surface, I've got a normal force. So that normal force is at a 90-degree angle to the force of friction, because the force of friction is parallel to the surface, and the normal force is always perpendicular. So now we're ready to start breaking these forces into their components. That's our next step as we solve this problem. So a couple things I want to ask you before we do that. First, what's making this object move downhill? Your gut instinct is to say it's the force of gravity. And you're right. But it's really hard to see that in this situation, right? This object is moving in this direction. The force of gravity doesn't appear to be acting in that direction. Another thing to consider is that we've got one force that's acting straight down in the y direction, and the other two are at wonky angles. So we're going to have to break two forces into components, which is a big old pain. Unless we turn our paper. You turn your paper. Now my force of friction is moving in the x direction. Now my normal force is pointing straight up in the y direction. Those two you can easily see are 90 degrees opposed from each other. And only one force is pointing off in a random direction. That's the force of gravity. If I turn this helps answer both of my two questions I just raised. I'll be able to break only one force into components, right? That's my only task here. I only have to break the force of gravity into an x and a y component in order to find the net force on this block. And my first question was, is it really gravity that is pulling this object downhill? And here we can see that that's true, right? We've got a y component. Oh, wait, hang on. That was super crooked. Let me see if I can erase that without ruining my whole picture. So, I've got a component that's equal and opposite to the normal force. So with that in mind, let me make my normal force a little bit bigger here, just to have that vector be approximately equal and opposite. So I've got a force of gravity in the y direction, and I have a force of gravity in the x direction. Now we can see, yes, the force of gravity is what's moving this object downhill. Look at what's happening here. Here's my direction of motion. And which force is acting left and right? The force of friction and the force of gravity. So this force is what started our object moving. We know a couple things already in advance of solving this problem. I'm going to turn my paper back while I write it down. We know that because this object is moving with constant velocity in all directions, we know that the net force in the x direction is going to be equal to 0 because we have no acceleration. We also know that this object in the y direction is not accelerating, so we know that the net force in the y direction is going to add up to 0. So even though I've got no numbers in my story problem here, those are two values that I have that are going to help as we go forward and solve. Okay, so here we go. So my next step now is to break my forces into components. So I'm going to go ahead and break the force of gravity into this y component and this x component. To do that, I've got a tricky bit of geometry I need to think through because I need to know what any of these angles are right here. I'm going to choose this angle right here. That's the one I'm going to choose because that's where the vertex is, right? I've got my force of gravity coming in this direction. I want to know what is that angle in there, right there. So here's where you've got a little bit of geometry to do. I'm going to go ahead and draw this on another piece of paper, I think. So I'm going to line like this. I've got a line like this. I've got a line like this. This is a right angle. Here's my angle theta. I know this angle has to be 90 degrees minus theta because the total in a triangle has to be 180, right? We're using the rule that a triangle has 180 degrees total. So let's add all of these up. 90 degrees plus theta plus 90 degrees minus theta. Let's check my math. I've got 90 plus a 90. Oh, that's good. That equals 180 plus theta minus theta. Well, that's great. That cancels those out. So I have, check, that my triangle is equal to 180 degrees total angle in there. That is not how a math person would do this proof, but it's good enough for me. So I know that this angle right here is 90 minus theta. Now I'm going to throw my wrench into the plans here, right? Which is, I'm going to go up here and as carefully as I can, okay, I think I did pretty good, draw a line that is perpendicular to the surface. So here, this is a 90-degree angle right here. We have a similar bit of math that we can prove right here. A line, like a triangle, which is something that you should contemplate occasionally and your brain should go, wait, what? A straight line also has a total angle of 180 degrees. And I know it's a little shiny, the ink will dry. So the total of all of these parts, this angle, and this angle, all add up to 180 degrees. We can figure out using the same math. I've got a 90-degree angle right here. I already, using my triangle, figured out this was 90 degrees plus theta. And all that together needs to add up to 180. So let's check it. I've got 90 degrees plus 90 degrees minus theta. What remaining thing? I'll call it x if you want, right? Plus x. So this unknown angle over here, x, this all has to add up to 180 degrees. Well, 180 degrees equals 180 degrees, ooh, minus theta plus this unknown angle. So let's go ahead and solve for x here, right? Minus 180 degrees. Love when I get to subtract the same thing. 0 equals negative theta plus x. Theta is just a measurement of that angle. It's just a number. I'll move it over there. I've got that theta equals x. That's an algebraic proof. We could also use the rules of geometry to figure out that same answer. So this angle right here is theta. To bring this back to our diagram on the previous page, here is where I got to get my colors right. Yeah. Here is where I had one side of my triangle, force of gravity in the x direction, and yeah, blue for the other one. This side right here is the force of gravity in the y direction. And this big line, the hypotenuse of my new triangle, was the force of gravity total. So I just did a little bit of work to show what angle is in my triangle right here. The same theta as the angle of my ramp that I measured with my level. Same. Go ahead and take a second. Make sure that that makes sense to you. Okay, so I'm going to go back to my physics problem. So my story problem right here, I've got that this angle right here is theta, same theta I measured with my level. So now I'm ready to find these components of the triangle. Okay, so I'm going to break into components. And in this case, we just have to break the force of gravity because I'm turning my scenario, right? I'm saying that this is the x direction, and this is the y direction. And I'll also say, make it easy, these are positive in those directions. Okay. All right, x and y components. So here we go. Let's start with the x direction. X, the force of gravity in the x direction, you'll notice, is actually the opposite side of my triangle from angle theta. Often, when we draw things, that ends up being the adjacent side. That's why it's important to pay attention to where is my angle theta, right? So I've got that the sine of theta, it's going to be my opposite, over my hypotenuse, is going to be force of gravity in the x direction, divided by force of gravity. I'm going to go ahead and multiply both sides by force of gravity. Cancel that out. So I have that the force of gravity in the x direction is equal to my total force of gravity times the sine of theta. So that is the value of my x component. In the y direction, I'm going to end up with the opposite thing, right? That's the adjacent side on my triangle based on where my angle theta is. So that's my adjacent side if I have my hypotenuse. I'm going to do the same math, which you can do yourselves. And if you can't, then, let me know because we'll practice that some more. So the force of gravity in the y direction in this example is the force of gravity total times the cosine. I'm trying to emphasize that it's in this example because these relationships entirely depend on which angle I'm using to do this calculation. In this case, I'm using that angle right there. So therefore, x is my opposite side from that angle. Y is my adjacent side from that angle. Okay? So now I can redraw my free body diagram. I'm going to do this so that I can make sure my forces really make sense. And I'm going to go ahead and, this is tricky for me to do with my camera setup that's here. So I'm going to draw it and then I'm going to lean my camera and turn it so that I can have both hands free to do that. So, just kidding. That'll be impossible for me to draw like that, all crooked and wonky pants. I'll just redraw it down here. I'll choose a different spot. So down here is where I'm going to redraw. Okay. So my free body diagram looks like this now. There's my object. In the y direction down here, I have the force of gravity, which is equal to the force of gravity times the cosine of theta. I'm going to write the whole thing out right now just because I want to make sure. I've got the normal force acting upwards. I've got the force of friction acting in this direction. And I've got the force of gravity in the x direction equal to sine theta. Oh, sorry, equal to Fg. Almost left it out, times sine of theta. Okay. So I've got this free body diagram, and here's where The comments I made before are going to be helpful for our drawing and for our understanding. The net force in the x direction, the sum of the force of friction and the force of gravity in the x direction add up to 0 because there's no acceleration in that direction. The force of gravity in the y direction, these two forces, normal force and force of gravity in the y direction, add up to 0. How do I know? Because there's no acceleration in the y direction. We're moving with constant velocity. Okay. So now we are ready to sum our forces. And this is where we can actually, I'm going to sort of set up these equations and we're going to start looking at the force of friction part. I'll probably break that into a second video just so that this isn't a billion hours long. So I already did this. So now we're going to sum the forces in the x and y directions. So you can do this on your diagram. You can do this in a table. Sometimes it's helpful to make a list. Okay. So in the x direction, I'm going to make sure that I pay attention to that I have these things in opposite directions, but I'm not going to put negatives in front of things because I'm going to let those values take care of themselves. Okay. Summing always means adding. Right? So in the x direction, I know that my net force is equal to 0 newtons, and that's equal to the force of friction plus the force of gravity in the x direction. Right? In the y direction, I know that my net force is equal to 0, which is equal to the normal force plus the force of gravity in the y direction. At this point, this is where we need to tackle the rest of our problem to look for values that we know and to see what happens. Okay, so I'm going to pause for real right here because I'm going to think for a second, decide if I make a second video or just continue right here. So let me go ahead and pause. If the video ends, you'll know that I decided to make a second video rather than continuing. All right, we're going to go ahead and just continue. We're ready now to start looking for the thing you actually wanted to find in this entire problem, which was the coefficient of friction. So this is how to solve a net force problem. If you had values, if you had other numbers, if you had data for these forces, you could go ahead and begin substituting these in and solving for the net force. If you need help knowing how to do that, we'll do that in a second or in another video. But now we want to go here and find this force of friction. In particular, what's the coefficient of friction for your specific lab situation? So I'm going to go ahead and flip to my new page, and I'm going to rewrite these equations right there. Okay. So, page. I'll mumble quietly to myself while I do this. Okay, so here's where we're at. In the x direction, I have net force equal to 0 because the force of friction plus the force of gravity in the x direction is come on computer, you do it. That's our net force, and they add up to 0. In the y direction, my net force is also equal to 0, and I've got my normal force plus my force of gravity in the y direction. I'm starting with my big global definitions or equations here, because then we're going to work our way down. We've got a few other things we need to bring in here before we complete this. You know a few other equations. Force of gravity is equal to a mass of an object times the acceleration of gravity. And that acceleration of gravity, you know, it's like the one and only number you should memorize, 9.8 meters per second squared. It's not negative, it's a number. You, the experimenter, determine whether you're going to include a negative on your force, depending on what your situation is. Okay, so this is a positive number. I add direction later if I need to. We also know this equation. The force of friction is proportional to the normal force. When you tilt a surface, it changes how much that object is pressing into the surface. You've experienced this. If you've ever dragged something across the floor, it becomes easier to move if you lift it a little bit as you push or pull it. You've changed the angle, you've changed the surface interaction, you've changed the normal force. Therefore, you reduced the friction. That's why it's easier to move a couch by lifting it and dragging it, so you're partly lifting it up, or why putting a rope on something to tow it pulls at an angle. So here are two equations that we know. So I'm going to go ahead and substitute in this equation. Since I'm looking for coefficient of friction, this is ultimately what I want to find. I'm going to substitute this equation in right here. So I've got that 0, my net force in the x direction, is equal to the force of friction. Oh, sorry. I just said I was going to substitute this in. I just went ahead and rewrote it. It's equal to the coefficient of friction times the normal force plus the force of gravity in the x direction. I'm going to write over here what my other equations were that I solved for in the last part. So I've got 4 equations that, and you'll notice force of gravity, normal force, force of friction, force of gx, force of gy. We've got each of our forces labeled there. So we actually have all the equations we need to solve this problem. So I'm going to also solve this equation right here. Because I know normal force plus force of gravity in the y direction adds up to 0, I'm going to go ahead and solve for normal force. Subtract force of gravity in the y direction from each side. So I know that, and I wrote this in a weird order, I'm sorry you guys, that normal force equals negative force of gravity in the y direction. See, I let my math take care of my direction from there rather than adding that in. So I'm going to go ahead and substitute this value, force of gravity, this is equal to the normal force. I'm going to substitute that in right there. 0 newtons equals coefficient of friction times negative force of gravity in the y direction plus force of gravity in the x direction. I'm going to expand this now, and I'm going to add in my 2 solutions from the last part where I found my components. 0 newtons equals coefficient of friction times a negative force of gravity times cosine of theta plus force of gravity times sine theta. Right? All I did was substitute in force of gravity sine theta for my x, force of gravity times cosine of theta for my y. I'm going to do another substitution. I know that everywhere where there's an Fg, that's equal to mass times gravity. And I'm actually going to do myself one favor here. This is my net force, right? I put the 0 in because it is 0, but it's a little premature, so bear with me here. I'm going to put in mass times acceleration. That's what Newton's second law says, right? So I'm going to go ahead and substitute mg in for my force of gravity everywhere. So here's what my equation looks like now. Mass times acceleration, my net acceleration. And this is kind of annoying to have this minus in here, so I'm going to flip these two terms. So I've got force of gravity. Here, I can write out what I just did. Force of gravity times sine theta minus coefficient of friction, force of gravity, cosine theta. So I'm just flipping the order of these two terms. Now I'll put my mg in. Mg sine theta minus coefficient of friction, mg cosine theta. Look at this happy equation right here. To quote Mr. P, everybody brought mass to the party. There's an m in this term, an m in this term, an m in this term, which means no matter what math I do, mass cancels out. If I divide both sides by m, because I'm solving for the coefficient of friction, mass cancels out. Mass is irrelevant. That's why you can do this lab at home without needing a scale. Mass is in every term, so it cancels out. As soon as I try to rearrange it algebraically, it will cancel. So now I've got an equation. Acceleration equals gravity. Acceleration of gravity times sine of theta minus the coefficient of friction times gravity cosine theta. This is just an algebra problem. I am solving right now for the coefficient of friction. So I'm going to work my way through that. And I'm going to not talk while I do it because it's just a lot. Well, I will talk. I'll just keep mumbling. Okay. I'm going to remove this term to the other side. Acceleration, here's sine theta. Coefficient of cosine theta. The minus 1 is driving me crazy. So I'm going to go ahead and flip this. Oop, oop. Right, I basically just multiplied each side by negative 1. Now I'm going to divide by g cosine theta. G cosine theta. Get rid of that. Just like that. So now, and remember, this is the whole side. Make sure you pay attention to what you're dividing the whole side. I've got that my coefficient of friction is equal to, I'm going to put my positive term first, acceleration of gravity times sine of theta minus my net acceleration divided by the acceleration of gravity times the cosine of theta. So, ladies and gentlemen, this equation right here will give you the coefficient of friction for any situation, any object sliding down a ramp. Our particular situation, this acceleration equals 0. So when we follow through with our particular situation in this lab, I've got g sine theta minus 0. Awesome. G cosine theta. So that just goes away. Now I've got g divided by g. That just goes away. So your coefficient of friction, and for those of you who are super mathy, right, we've got sine over cosine. Isn't that tangent? There you go. Here's what the physics of this equation means. So this is your answer right here, right? So, or, or you could do it with the tangent there. What this equation says is how much friction there is. You want to measure the friction in your situation. It depends on the angle. It doesn't depend on the mass. It depends on the angle. And we know that to be true. Your job is to achieve the 0 acceleration. That's how you get to use this simple math relationship. You have to get constant velocity in your lab if you want to be able to use this equation. Otherwise, you need to measure your acceleration and use this equation in the orange box instead. There you go, everybody. That would be the math for how to do.